So, there are the following things that we demand of this concept of norm or magnitude. Let us write them down. This is a useful and a powerful idea to have around us. So, what do we want of a norm? So, if I have a vector x, essentially a sequence x n, n over the set of integers, then its norm, which we shall denote in the following way, we will denote it like this, should be essentially the dot product of x with x square root. And further, we would want norm of x to be non-negative, and if at all the norm of x is 0, that implies and is implied by the sequence itself being 0 everywhere. That is, x of n is equal to 0 for all n belonging to the set of integers. This is important. So, we do not want that norm to be 0 unless the sequence itself is the 0 sequence. A non-zero sequence, even if it is non-zero at one point, must have a non-zero norm, and a 0 sequence must have a 0 norm. Does our dot product satisfy this? Well, for real sequences it does. If x n is real, or rather if x 1, x 2 are real, and we take the following definition, the dot product of x 1 and x 2 is essentially summation on n going from minus to plus infinity x 1 n, x 2 n. Then the dot product of x with x is essentially summation n running from minus to plus infinity x squared n, and as long as x n is real for all n belonging to z, this is this satisfies the requirements of norm. It is non-negative and it is 0 if and only if the sequence is identically 0. But what if this is complex? So, we have to allow complex sequences too. One of the coordinates could be complex, and in fact, the situation could be such that x squared n could be plus 1 for one of the coordinates and minus 1 for some other coordinate in that case, because when you square a complex number, nothing guarantees the output is going to be non-negative. In fact, nothing even guarantees the output is going to be real. Where is the question of non-negative? So, this definition is not going to work when x 1 and x 2 are complex sequences in general, and we need to tweak the definition a little. Well, it is not that difficult. After all, what we want is that for every coordinate you must get a non-negative quantity when you take point by point products. So, all that we need to do for that purpose is to complex conjugate the second argument in that summation. So, the small change for complex sequences will do our job. Dot product of x 1 with x 2 is summation over all n x 1 n x 2 bar n, where bar denotes the complex conjugate. Now, one point to note here when we make this little change is that commutativity property is lost. So, if I take the inner product x 1 with x 2 and then if I take the inner product x 2 with x 1, there is a complex conjugate relationship. And this is the more general requirement of a dot product. In fact, this is the simplest way in which one can define a dot product between sequences. There are many other ways, again an infinite number of ways, but at this moment we shall not go into the other ways, they will only confuse us. This is what is called the standard inner product, but one can have many other non-standard inner products which obey the following conditions. The first condition is this that we write down here. The inner product of x 1 with x 2 is the complex conjugate of the inner product of x 2 with x 1. Secondly, the inner product is linear in the first argument. In other words, if I take a 1 x 1 plus a 2 x 2, where in general a 1 and a 2 could be complex and take the inner product with x 3, it is essentially a 1 times the inner product of x 1 with x 3 plus a 2 times the inner product of x 2 with x 3. This is the second requirement of an inner product, linearity in the first argument. The third requirement of the inner product is what we have been building towards all this while, namely what is called the positivity or non-negativity. In fact, positivity is more appropriate. Positive definiteness, namely the inner product of x with x is always greater than or equal to 0, and x equal to 0 implies and is implied by the inner product of x with x being 0. In fact, any operation between two sequences x 1 and x 2 which obeys these three conditions is called an inner product, and the standard inner product that we have just described is one such, which we shall use very frequently. So, in the discussions henceforth, when we say inner product of sequences, we mean the standard inner product unless otherwise specified. All right. So, let us just verify this for completeness. Let us verify this for the standard inner product. The inner product of two sequences x 1 x 2 is essentially the sum n going from minus to plus infinity x 1 n x 2 bar n. Definition. The first property, as we said, is complex conjugate, easy to verify. So, in fact, I will leave it to you as an exercise. Verify the properties of what is called conjugate commutativity, the first property. And linearity. Linearity in the first argument. I leave it as an exercise, easy enough to do. But we shall, because it is so important, verify the third property, the positive definiteness. Indeed, if we take the dot product of x with x, it is summation n going from minus to plus infinity x n bar, which is summation n going from minus to plus infinity mod x n squared. And it is very easy to see that this is equal to 0 if and only if x n equal to 0 for all n. Even if one of the coordinates is non-zero, that particular mod x n squared is going to be non-zero and it is going to contribute a positive term. And of course, it is very easy to see that each term for every n, I mean, is strictly positive if x n is non-zero. So far, so good. So, now we have built up the idea of inner product or dot product between two sequences, which is going to be useful to us. So, we have moved from 2 dimensional to 3 dimensional to n dimensional, n is finite, and then to countably infinite dimension. Now, let us move to uncountably infinite dimension. So, suppose I take a function of the continuous variable t. How can I extend these notions? So, extension to uncountably infinite dimension. Well, this is going to be very difficult in general, but very easy in particular if we simply accept that every t for real t is a different dimension. Simple. So, if you have a function x of t, t over the real numbers, x of t for a particular t is the tth coordinate, so to speak. And there is an uncountably infinite number of such coordinates indexed by the real numbers. So, in principle, in a given function, you have complete liberty to put down the value of x t at every different point t. The only catch is we have agreed that we would like to make the function square integrable. So, that does put some restriction on x t, but not a very serious one even so. Now, dealing with infinite dimensional spaces, if we wish to do it very rigorously and very, very carefully and to satisfy the fastidious mathematician is a difficult job. And we do not really intend to do that all the way in this course. If some of us do wish to take that puritanical perspective, one of course would benefit from it in some ways, and one could look up a book on functional analysis. But what we wish to do is rather to give intuitive understanding of some of the concepts at different places. The intuitive understanding will not be different from a more rigorous understanding for those specific situations, but it may not quite be complete. Even so, we would not suffer too much in our study of wavelets, in our applications of wavelets, if we take this intuitive path to some extent, not all the time. I mean to some extent in the context of dealing with infinite dimensional spaces.